Evan here, and last time we started talking about sort of types of reactions, and we were talking about really two categories of reactions. There's double displacement reactions, which is really where we were at, and there's really redox reactions, which hopefully we'll get to as well. And again, double displacement reactions are always two ionic compounds together. So that is really how you can recognize that it is a double displacement reaction. And in that particular case, 100% of the time, what always happens is our two positive guys will actually switch partners. And the result of that is you'll form two new ionic compounds on the product side. And really, double displacement reactions, as I mentioned last time, is you can think of it as sort of as a big umbrella of reactions, big sort of classification. And there's going to be more specific ways to classify reactions that sort of fall underneath that. One we started talking about last time, which is a precipitation reaction, much like you probably did in lab today. That means that you got some type of solid that basically forms. So the result of these ions basically switching partners will result in a solid precipitate being formed. Another sort of version of a double displacement reaction that we'll talk about here in just a second are acid-base reactions. And acid-base reactions actually, for the most part, will produce water. And those are really two of the three reasons why a reaction pretty much takes place. As we talked about last time, there's really three reasons. One being a solid is formed, one being you made water. And when we get to our redox here, the third reason a reaction really takes place is a transfer of electrons. Now, we were talking about precipitation reactions, and we actually talked about at the end there three different sort of equations that you could write for a particular reaction. And that is, for example, I think we were looking kind of like the one you were doing in class there or in lab. Take a little potassium iodide plus some lead 2 nitrate here. You will get, again, this is a double displacement. Those guys are going to switch partners. A little PbI2, which is a solid, and a little KNO3. Obviously, it's an equation, so we always want to make sure that we do balance it here. So a 2 there and a 2 there, I think should do it. And this is, again, like a normal equation. This is what is sometimes referred to, obviously, as the molecular equation. But when these guys really do kind of go for a swim in the beaker there, because these are strong electrolytes, these two here, they are going to 100% break apart into ions. So if you were to sort of look at the beaker, if you put both of those things in, the Ki and the lead 2 nitrate, what you would actually have sort of in that beaker is some lead ions and iodide. You would have some, lead, potassium and iodide, and lead and some nitrate ions basically floating around in that solution. And we could write an equation that represents that. This would be 2K plus. Again, that 2 would get distributed to both guys there. You would get 2I minus. Again, being a strong electrolyte, which most ionic compounds are, will 100% break apart into those ions. We will get lead with a plus 2 charge floating around. We will get a couple of nitrate ions floating around. And again, this 2 kind of comes to the front when we break it apart. Tells us we have 2 of those nitrate units. Remember that when we write this type of equation, anything that is a solid, a liquid, a gas, or really a weak electrolyte will stay together. So our solid would actually stay together here. And here we would have this ionic compound basically breaking apart into our ions here. And this is what is sometimes referred to as the total ionic equation. It basically represents pretty much what's sort of happening in that particular beaker. And what's happening in that beaker is these two guys will then want to come together, and they will come together and make that, well, it's yellow, but we'll go with red today. It'll make that yellow sort of solid that you will make, and they will stay together here as obviously the lead 2 iodide. When we look at this equation, we'll always find some ions on both sides of the arrow that look exactly the same, and you should have really the exact same number of those ions as well. So we have 2 potassiums there. We got a couple of nitrates. And these guys are what are referred to as spectator ions. And you can kind of see in my picture here, that is that guy and that is that guy. They're just hanging out, floating around, watching what's going on. They're not really leading to any product being formed in this reaction. Frankly, they're there just to sort of balance out the charge of everybody. We typically will cross out those spectator ions, and we're left with really a third type of equation, which is known as the net ionic equation. And the net ionic equation pretty much tells you exactly what is happening in this reaction. It is, again, really the lead that's coming from that lead 2 nitrate. It's going to go find those iodide ions, and they're going to come together basically to form this solid, which again is really the reason why this reaction takes place. So we have a molecular equation which we just write like normal with all the formulas. We have a total ionic equation where we break apart anything that is a strong electrolyte, and we keep together things typically that are solid or liquid or a weak electrolyte. And we find our spectator ions, we get rid of them, and what we're left with is the net ionic equation, which is really the equation that, like I said, pretty much describes what is actually happening in this reaction. Any questions on any of that stuff there? Yeah. This obviously is a precipitation reaction, which is a more specific classification of a double displacement reaction. It is obviously a double displacement reaction, but more specifically could also be classified as a precipitation reaction because we get this solid that forms, which again is one of the 3 reasons why a reaction takes place. So how do we know? And again, this is the one we just looked at here. Maybe we'll get there. Come on, there it is. So how do we know if we put together these ions, if we should expect something to make a solid or really not make a solid? And we use what's known as solubility, or really what are referred to as solubility rules, to help us decide whether or not when we put these 2 ions together, should we expect a solid to form or not. Solubility in general is the maximum amount of solute that can be dissolved in a given amount of solvent at a specific temperature. What we're talking about here again is aqueous is a solution, which is really a homogeneous mixture that we talked about. And there's really 2 parts to the solution. If you remember, we talked about a solute, which is the smaller part, and a solvent, which is the larger part. And I think the example we did was, water and some sodium chloride will make a sodium chloride solution. And again, water here would be our solvent, and our sodium chloride would be our solute. So temperature does play a role, for example, with solubility. Usually the higher the temperature, the more soluble a solid is in a liquid. Lower the temperature, usually the opposite of that. So when we look at solubility rules, there's really sort of 3 distinctions that we see. Most of the time we usually just see 2 of them. But one is something being soluble, and what that means is if something is soluble, you would not expect a solid to form. And those would be the guys that would get the aqueous symbol next to them, which means that we do not have a solid. It's basically a solution. Everything should dissolve. You shouldn't see any type of solid form. Now, if you look at the solubility rules and it says it's insoluble, that means you should expect a solid to form, and you would get a solid being happening here, and it would get the S sort of indication. Now, the last sort of description there, you do occasionally come across, and that is what is known as something being slightly soluble. And pretty much like the name implies, it is slightly soluble. It will dissolve a little bit, but it mostly will not dissolve. So most people consider slightly soluble to be more like insoluble than soluble. So usually, in most cases, you could kind of consider slightly soluble as being insoluble in that case. As you'll learn if you go off to 1B at some point, even though we look at some of these rules about solubility, they're not 100% always going to occur. So solubility is affected by a lot of things like pH, things like concentrations can affect solubility. So even though technically solubility rules tell you if you put these two things together, you should always get a solid. The reality is you may not always get the solid depending on some other conditions. But for this class and the next class, you could think of it as always going to be solid and stuff like that. But in reality, there is some other factors that come into play. So these are a table here, or a list of some solubility rules, and obviously here at the school they want you to know everything, so you do need to know the solubility rules here. So let's talk about these guys here. These are things that will typically be soluble. So these are guys that typically will not form a solid and should get the aqueous sort of designation next to them. If you see anything from group 1, it is not going to be soluble. I'm sorry, it is going to be soluble in everything. So it is soluble in everything, no matter what the situation is. There's no exceptions, which means as soon as you come across something that has, say, like sodium in it, you automatically know that it's going to be soluble and should not make a solid. Anything with ammonium in it, NH4 plus, is also going to be soluble. There are no exceptions. So once again, if you're looking at a formula and you see ammonium in it, you automatically know that it's soluble and it should have an aqueous next to it. Anything with nitrate, chlorate, perchlorate, even acetate, which might not be on this one, these guys are also going to be soluble in everything. So there are no exceptions, which means, again, as soon as you see it in a formula, you really don't need to look any further to try to decide if you're going to get a solid or not. You should not get a solid in that case. Now, when we look at things like chlorides, bromides, and iodides, Cl, Br, and I, they are soluble in everything, and they should normally get an aqueous sort of symbol. But in this case, though, there are actually 3 exceptions. So if you have a chloride, a bromide, or an iodide that happens to be hooked up with silver, that's mercury 1, and that's also lead 2, then it will actually do the opposite of what it normally does. So normally they're aqueous. That means if you have any of those 3, they would then become insoluble and would be a solid at that point. Most sulfates are going to be aqueous in everything. There are some exceptions. Silver and calcium sulfate, they are slightly soluble. Barium and mercury 2 and lead 2 sulfate really are insoluble. Once again, slightly soluble mostly means insoluble. So these are the rules that you could use to help you decide that, like, if you're going to put these 2 ions together, which happens obviously a lot with double displacement reactions when you're looking at a precipitation reaction, would you expect a solid to form? Now, there's also some things that are typically insoluble. So typically, if you have these guys in formulas, they're insoluble, which means you will expect a solid to form. So you'll get a solid that's going to happen here. The first one is hydroxides. So anything with OH minus is typically insoluble, except anything that is from group 1 on the periodic table, and anything like barium and calcium are slightly soluble. So this exception is actually the same rule that we had on the previous slide. The first rule on the previous slide was anything from group 1 soluble. So anything that has group 1 in it is still going to be soluble. That is why when we look at something like sodium hydroxide, it is soluble because hydroxides are normally insoluble, but in this case, it is hooked up with somebody from group 1, which means group 1 is always soluble. So that is why something like sodium hydroxide is a solution and is soluble in this case. Carbonates, phosphates, and sulfides are typically insoluble, except for the same sort of rule we had on the last slide, which is if they're hooked up with somebody from group 1, or if they're hooked up with ammonium, then they will be soluble and not insoluble. So if you had something like ammonium sulfide, this would be soluble. Sulfide is insoluble, but ammonium is soluble in everything, so it would be soluble. If you had a little bit of iron 2 sulfide in this case, sulfide's insoluble except for group 1, which that is not, or ammonium, which that is not either. This guy would be insoluble and would make a solid in this case. Question on that there. Here is a solubility table instead of in words, more like a table sort of version of it, which might be easier to sort of look at and sort of remember. Again, here, everybody over here is going to give you something that should be aqueous and no solid. If you have these exceptions for these guys here, then you will get a solid that will form. If you got somebody over here, typically it's going to be insoluble. Again, unless you have these exceptions, would make these guys soluble in that case. So these are the rules that you could use. So for example, if we had a little silver nitrate plus some sodium chloride, again, this is a double displacement reaction. Our guys are going to switch partners basically. And our silver and our chloride would come together, and our sodium and our nitrate here will come together. We could use these rules to help us decide, again, if something's going to be a solid or not. So if we take a look at it, I may not be able to find silver by itself on this list, but I definitely can find nitrate, and nitrate is right there. It is soluble in everything. There are no exceptions. So as soon as I see that nitrate, I know I am not going to get a solid, and this guy should be aqueous. I come to sodium, and frankly, that is as far as I need to look, because sodium is group 1. Everybody in group 1 is soluble in everything. There are no exceptions. That is basically right here, group 1, no exceptions. And that is all I need to look at. You could also look at the chloride, which is soluble in everything except for these guys. And in this case, is hooked up to sodium, and it's not one in the silver, lead, or mercury. Coming over here, chloride is soluble in everything, but there are 3 exceptions. And this guy right here makes it one of those exceptions. So instead of being soluble, it's the opposite. And this guy would be that white solid that you typically will see when you do this reaction. Lastly here, if I look at sodium, frankly, that's as far as I need to look. I know it's going to be soluble. I could also look at nitrate if you like as well, which is also going to tell me it's soluble. So this is how we could use these solubility rules to determine if we would get a solid or not. In this case, we actually did get a solid, which means this is a precipitation reaction, and this is still obviously a double displacement reaction. First off, any questions on how to use the solubility rules there? We once again could look at this reaction, and we could go through our 3 reactions. And again, we had our silver nitrate, our sodium chloride, making our silver chloride, plus our sodium nitrate here. And again, that is our molecular equation. We could write our total ionic equation here. That silver nitrate is a strong electrolyte, which means it will break apart into a silver ion and a nitrate ion. Sodium chloride will also break apart, as it is a strong electrolyte, into a sodium ion and a chloride ion. Once again, our solid will stay together. And this, guys, is going to break apart, as it is a strong electrolyte, into sodium and nitrate here. Once again, looking at our total ionic equation, we can see that nitrate and nitrate are the same. Sodium and sodium are the same. These again would be our spectator ions. We again can cancel them out, and we get our net ionic equation, which is going to be the silver ion from the silver nitrate going to go find the chloride ion from the sodium chloride. They're going to precipitate out of solution as silver chloride. So again, if you toss those guys into a beaker, you're going to get silver and nitrate. And if you popped your sodium chloride in there, you're going to get sodium and chloride. Once again, these two guys are going to find each other based on the solubility rules and precipitate out. Once again, as you can see in this picture, it's just the sodium and nitrate floating around as our spectator ions, not contributing to our product being formed. Any questions on that there? So let's take a look at acid and base reactions. Acid and base reactions are also still double displacement reactions. So under the big category of double displacement reactions, we have precipitation reactions, which is a more specific classification of a reaction that forms a solid. And acid-base reactions they're sometimes referred to as acid-base neutralization reactions, are a more specific classification of a double displacement reaction that actually will form water in this case. So this is usually what you'll get here is the formation of water. Acids have sour taste. Don't taste them. They do cause litmus paper to turn usually to red from blue, for example. They do react with hydrogen, certain metals to form hydrogen gas. You might have did this one today, a little magnesium plus some hydrochloric acid. Going to do a little single replacement reaction here. Going to make some magnesium chloride and generate some hydrogen gas. Again, a little 2 there. That hydrogen gas is the bubbles you saw, perhaps. You put your thumb over it, it lights a splint, right? And pop, pop sound or whatever, barking dog. And that is, again, the hydrogen gas being ignited here in this reaction. Aqueous acids are strong electrolytes and weak electrolytes. Once again, those are things that can conduct electricity. A reminder I think we've talked about before, but just one more reminder of there is a list of kind of like 6 strong acids, which is a really good thing to sort of know. Again, that's your hydrochloric acid, your nitric acid, your hydrobromic acid, hydroiodic acid, sulfuric acid, and who did I miss there? Perchloric acid. This list of 6 strong acids are really good ones to know for a couple of reasons. You do come across it a lot in all your chemistry classes you're going to take. But you could use this list, if you know these 6, as a process of elimination for anything that is not one of those 6. So if you come across an acid that is not one of those 6, it's probably a pretty safe bet that that's a weak acid. So for example, some weak acids, hydrofluoric acid, acetic acid. These are weak acids, and as you can see, they're not one of those 6. So again, if you come across those guys, you would know that you're dealing with a weak acid. Again, a strong acid is a strong electrolyte going to 100% break apart in solution. Weak acid is going to basically be a weak electrolyte. It's going to mainly stay together, but produce a little bit of ions in solution. Bases, on the other hand, have a bitter taste. A lot of soaps, like drain cleaner, are bases. They change litmus paper to blue when you touch them. So you did maybe the calcium water one today or whatever it was, and that should have turned your litmus paper blue because it made calcium hydroxide, which is a strong base. Aqueous solutions could have strong bases and weak bases as well. Most of our strong bases are going to be from group 1 and 2 on the periodic table that have hydroxide in them, like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. So a lot of the strong bases pretty much going to have hydroxide in the actual formula, and probably a metal from group 1 or 2 is probably a safe bet that that's going to be more of a strong base. I would say probably your popular weak base for the most part is ammonia is probably the most popular kind of weak base that people use as an example of a weak base. And ammonia is definitely a weak base. So an acid's really purpose, if you will, is to be able to donate an H plus into solution. So an acid is something that can really produce free H plus in solution. So the ability of an acid to essentially produce those H plus ions floating around in solution that's not attached to anything. And that's what makes something a strong acid. So like HCl, if you took HCl and you dumped that thing into a beaker and it dissolved, you would have nothing but hydrogen ions floating around and chloride ions floating around. You would have none of the HCl units sealed together. And this is why it's a strong acid, because frankly, it just needs to go for a swim and you're going to produce a lot of H plus really, really quickly. And that's going to make that solution pretty acidic because there's a lot of free floating around H pluses. And that's different than, say, something like HF, which is a weak acid. If you dumped HF into a beaker, you would actually have a majority of HF units sealed together. It would break apart just a little bit, so it is still able to produce some H plus in that solution, but it would not be able to produce anywhere near the amount of H plus that like HCl can do. And that's why it is considered a weak acid. It's still considered an acid because it still has the ability to produce a little bit of H plus, but again, nowhere near the amount that you would get if you dumped the hydrochloric acid into that solution. Questions on that there. Now, bases, on the other hand, are things that have the ability to produce hydroxide in solution. So just like our acids, if something is a strong base, that is basically what it's able to produce in the actual solution. Once again, it's free OH minus just floating around, not attached to anything, and that makes something a strong base. So once again, if you dumped your sodium hydroxide, which is a strong base, it's 100% going to break apart into sodium ions and hydroxide ions, basically. And in this case, you will not have any of that NaOH unit still together. It's going to completely pop apart into ions. Here you produce a lot of hydroxide ions really quickly. Hydroxide OH minus and H plus, they're actually related to each other in the sense that as one goes up, the other goes down. So when you add something like a strong base to a solution, you just populated it with a lot of OH minus that shot up really high. The H plus concentration went down a lot. And the result of that is you actually will probably go more basic in terms of your pH because you have a lot more of OH minus in that solution than you do H plus. And you'll definitely have a basic solution. Once again, if you dumped in there some ammonia, which is a weak base, it would mainly stay together, but will still have the ability to produce a little bit of hydroxide. And because it still has the ability to produce a little bit of hydroxide, it is able to be considered a base, but again, it will not produce anywhere near the amount of hydroxide that something like sodium hydroxide can actually produce in solution. Any questions on that there? So what happens when we react these two things together? When you take a strong acid and a strong base together, you essentially always make two things. You pretty much get a strong acid plus a strong base will always produce a salt and water. And once again, a salt is a fancy word for basically an ionic compound. So you could take any strong acid and strong base combination you like, and pretty much what you're making is essentially water, which is why this is sometimes referred to as a acid-base neutralization reaction, because ultimately what you're making is water. And water, as you remember, again, is one of the three reasons why a reaction takes place. So the formation here of water is why this reaction is taking place. So for example, if you took a little hydrochloric acid, which is a strong acid, and you react it with sodium hydroxide, which is a strong base, you again will see a double displacement reaction, which this is, again, positive, negative, positive, negative. We're going to switch partners here. These guys are going to come together, and these guys are going to come together. And the result of that is we will make sodium chloride, which is aqueous because there's sodium in it. And we will make water, which is a pure liquid. And this is our salt, and obviously this is our water in this particular case. That is the molecular equation. We can again write a total ionic equation for this. Since HCl is a strong acid, it will break apart into H plus and Cl minus. Sodium hydroxide being a strong base will break apart into Na plus and OH minus. Our sodium chloride also going to break apart into sodium ion and chloride ion. And much like the solid here, the water is actually going to stay together, otherwise it wouldn't be water, so it's actually going to kind of stick together. This would be our total ionic equation in this case. We again could look on the left-hand side and right-hand side, and we could see that on the left-hand side we got a chloride. On the right-hand side we got some chloride as well, and we got a sodium ion and a chloride ion. These again are our spectator ions. By the way, the spectator ions are pretty much where you get your salt from. Yeah, the guys just floating around hanging out. That is where you get the salt part from. We cancel those guys out, and we get our net ionic equation, which is the H plus from the acid goes and finds the OH minus from the base, and we form some water basically here. And again, that is ultimately what is happening in this reaction. Once again, if you want the beaker view of it, you toss your HCl in, H plus and Cl minus. You toss your sodium hydroxide in, sodium and hydroxide. Again, these guys are going to come together. I'll just kind of hash it out. That's going to make our water. As again, you can see our chloride and our sodium are just hanging out, floating around, which is our spectator ions, and really the salt part here. Our salt here is aqueous, so it's really not together. They're actually just floating around freely in the solution, really surrounded by waters, basically, in that idea. No matter what combo of strong acid and strong base you put together, that is always the ending there, is basically you get the H plus from the acid, OH minus from the base, you make water. So you take any combination of strong acid, strong base, that is ultimately always going to be your net ionic equation, which is that formation of water. Any questions on that there? So as I mentioned before, again, we have our spectator ions and water being our ultimate endpoint there. I would say probably 99% of the time, based on solubility rules, you will basically always have a salt that is soluble. It is possible to get an insoluble salt, but most of the time, that salt, like sodium chloride there, or in this case, potassium chloride, will most likely always be aqueous. And again, if you took this one, which is our nitric acid, which is a strong acid, and potassium hydroxide, which is a strong base, you went through our three equations, you will once again end up with this as your net ionic equation, basically that formation of water that's basically happening. Any questions on that there? Now, what would happen if we actually had a weak electrolyte involved? And I would say most weak electrolytes are probably weak acids and weak bases. So let's just say that we did this reaction with a weak acid versus obviously what we've seen here with a strong acid. So if we took something like hydrofluoric acid, which is a weak acid, and reacted it with sodium hydroxide. Once again, this is an acid-base reaction. It is also still a double displacement reaction. We're still going to switch partners here. So once again, we're going to get there and there. That is going to get us our NaF. I know this is going to be aqueous because there's sodium in it, so it should be soluble. We will again make our water in this case. Bless you. And this would be our molecular equation. When we get to our total ionic equation, it is going to be a little bit different. Because HF is a weak acid, it means it's a weak electrolyte, which means when you do dump that HF into this solution, it is mainly going to stay together. You will get a little bit of it breaking apart, but it mainly is going to be this guy in that solution. And because of that, we would not break it apart when we get to the total ionic equation. We would actually still leave it together because it's a weak electrolyte. Our sodium hydroxide is a strong electrolyte, which means it will break apart into sodium ions and hydroxide ions. So we will get those sodium ions and hydroxide ions basically floating around in this solution. On this side, the sodium fluoride would break apart. And once again here, water will actually stay together. So again, anything in a solid, liquid, or weak electrolyte pretty much will stay together. Now when we look for our spectator ions, it's a little different. We actually only have one spectator ion. That's it. That's the only one same on both sides. So that is our spectator ion here. If we cancel it out, that's going to leave us our net ionic equation that will actually be HF plus the hydroxide, going to make F minus and our water. So again, essentially what's happening here is that little bit of H that comes off, we're going to kind of make that, and you can see we're left over with some sodium ion floating around. That's our spectator ion, F minus and HF, basically left over in this case. Any questions on what to do if it's a weak electrolyte? All right, questions on total ionic equations, net ionic equations, molecular equations. Need to be able to write all three of those, find the spectator ions. By the way, again, total ionic equations, net ionic equation for any formula that is an ion, it needs charges, yeah? It's because they are ions, so you need to have the charges. So you got to have where it says OH minus, the minus, where it says F minus, you got to have that minus there to be correct with our charges. Any questions on double displacement type reactions? So again, double displacement reactions takes care of two of the three reasons why a reaction takes place: formation of a solid, formation of water. So let's talk about what takes care of the third reason a reaction takes place. And these are what are commonly referred to as redox reactions. And redox reactions involve a transfer of electrons. So that's basically what redox means. Redox means oxidation and reduction is basically what it means. There are several different definitions of oxidation and reduction, but we'll talk about really the two definitions that sort of relate to mostly what you'll see in here. And that is, if something is oxidized or goes through oxidation, it means it has lost electrons basically. And if something is reduced or goes through reduction, it means it has gained electrons. There are other definitions of oxidation and reduction, which when you get to organic chemistry, you'll learn, and it has to do with oxygen and hydrogen. But for us in general chemistry, usually these are the definitions we look at. Now, what does that mean? Well, it means that if somebody loses electrons, do they become more positive or more negative? What do you think? If you lose electrons, you become more positive, right? Because you now got more protons than electrons. And if you gain electrons, you become more negative. And one way, by the way, you could remember maybe oxidation and reduction is sometimes people are fond of the oil rig. Oxidizing is losing, reducing is gaining. I'm old school. We learned Leo the lion goes grr, right? Loss of electrons is oxidation. Gaining of electrons is reduction. You can put them together, put Leo the Lion on the oil rig, and he'll go grr, right? And you don't have to choose. You just remember the whole sunny in there. But how do we know really if something's being oxidized or something's being reduced? Really what you look at is what is known as the oxidation number or state. But for our purposes, we'll just kind of call it the charge, even though really it's not the charge, but we'll just call it that. But really what you're looking at is the oxidation number or the charge of an element on the left-hand side of the arrow to what its charge or oxidation state is on the right-hand side of the arrow. And that will allow you to understand if something's being oxidized or reduced. How can you simply figure that out? Well, I'm a big fan of the basic number line. And to the right of 0 are positive numbers, I think, and to the left of 0 are negative numbers. So if somebody's being oxidized, what you will see when you compare those oxidation states from the left-hand side of the arrow to the right-hand side of the arrow is it should become more positive. So if you're moving along the number line in this direction towards the positive side, whatever you're looking at probably just got oxidized and going through oxidation. Now, if somebody's gaining electrons, they're going to become more negative. So if you compare the left-hand side to the right-hand side, and you're moving this way on the number line towards the negative side, then that guy got reduced or went through oxidation, or went through reduction. One of the nice things about oxidation and reduction is it always happens together, which means if somebody's getting oxidized, somebody else is getting reduced, which means all you have to do is figure out one of those things, and then the opposite thing's happening to the other guy that's there. So if you could at least for sure, and you're confident about it happening to one of these things, then you can actually figure it out. So what are we talking about? Let's just take a simple example here. We got a little sodium metal plus a little chlorine gas. Gonna make a little salt for the fries, right? Some sodium chloride here, put a 2 there to balance it since we're in chemistry class. There we go. We got a 2 there as well. So what we want to look at, like I said, is really the oxidation state on both sides of these elements, but we'll just think of it again as the charge. If I have sodium metal by itself that is not combined with anybody else, does it have a charge? The answer is it does not have a charge. So you can take anybody off the periodic table by themselves, not combined with anybody else. They will not have a charge or a zero oxidation state. So this guy has basically a zero oxidation state, no charge. Chlorine, that is naturally how chlorine comes as a diatomic molecule. It is not combined with anybody else. It pretty much has a zero oxidation state as well. So again, anybody uncombined from the periodic table, that's what you're basically starting with, is a zero. These guys only get charges when they hook up, like what happens here on the right-hand side of the arrow. On the right-hand side of the arrow, we have an ionic compound, and that sodium is group 1, which means it has a +1 charge, right? And the Cl is group 7, which means it has a -1 charge. So this is how you could use the number line to sort of help you understand what is going on. So if I were to, for example, here, look at the sodium. Sodium on the left-hand side is starting at 0, which is right about there. Sodium on the right-hand side ends up at +1, which means it's moving in this direction. That means the sodium is moving in the positive direction, and that means that sodium is being oxidized or reduced in this case. It is being oxidized, right? It is going through oxidation, is becoming more positive as it goes from the left-hand side of the arrow to the right-hand side of the arrow. Now, one of the nice things about this is if I'm confident that sodium is being reduced or being oxidized, by default, this guy right here has to be reduced or going through reduction. But you could also do it for the chlorine. If we look at the chlorine, it started at 0, which is about here, and it ends on this side at -1, which means the chlorine is moving in the negative direction, which means it is gaining electrons and going through reduction. What is being oxidized, what is being reduced is on the left-hand side of the arrow. And this is what is considered a redox reaction because there is an electron transfer. We know what's actually happening here. It is the sodium That is going to send some electrons over to the chlorine, and they're going to accept it. We also should know that whenever you have a metal like this and a non-metal, metals typically do what with electrons? Gain or lose them? Metals typically lose electrons, which is why they become cations, positively charged. So metals should always be the one being oxidized in this situation, and nonmetals are always the ones that gain electrons and become negatively charged anions. So whenever you have a metal and nonmetal coming together like this reaction, you should always know that the oxidation guy is going to be the metal, and the nonmetal will always be the one being reduced because it's going to be the one gaining those electrons. Any questions on that there? Now, you may be saying, what happens if you don't have a non-metal involved and it's just like metals on both sides, right? You could still use this method. So let's just say I had an iron on the left-hand side of the arrow that started at a +3. And let's just say I ended up with an iron with a +2 on the right-hand side. So you take a moment and decide, is it being oxidized or being reduced, this iron? All right, so let's take a look. I'm going to steal this number line here. So really we're looking at the iron. It starts on the left-hand side at a +3, and on the right-hand side it ends at a +2. +3 is somewhere in this ballpark, and my iron ends up at a +2, which means it is moving in this direction. It is becoming more negative, which means this guy is actually going through reduction, right? And is actually being reduced in this case. So again, even if there's no non-metal involved and you're trying to compare again a metal on each opposite sides, you can use this kind of number line. Again, if it is moving in a negative direction, that substance is being reduced. And if it's moving in a positive direction, that thing is going through oxidation. Any questions on how to do that there? Okay. All right, so that is what we were just talking about there. Here we're seeing an electron transfer from, that electron totally missed, from our sodium to our chlorine. And again, that's the one we just did there. That is a redox reaction. Now, this is also one that you did today, right? Watch what happens, but don't stare directly at it. Otherwise, it makes for a very spotty afternoon of looking. That is magnesium. You burn it in a Bunsen burner. It gets very bright really quick. And if this is also a redox reaction, if we take a look at it, this is magnesium not attached to anybody. So it has a 0 oxidation state. This is oxygen, how it naturally comes, also has a 0 oxidation state. When those two guys come together to make that white little powder that forms when you do that, the magnesium is group 2, which now has a +2 charge. Oxygen is group 6, which has a -2 charge. Once again, if you just take a peek here at our number line, magnesium started at 0 and ends at +2, becoming more positive. So once again, as we would expect here, this is going through oxidation. And by default, this guy has to go through reduction. And we can see that as well. Oxygen starting at 0 on the right-hand side ends at -2, becoming more negative in this case. And it is going through reduction. This is also a redox reaction that's occurring. Electrons, again, are being transferred in this fashion here from the magnesium basically to the oxygen. Any questions on that there? You can actually write two what are referred to as half reactions to identify what is being oxidized and what is being reduced. When we write these half reactions, they are half of what is happening. This is the oxidation half reaction. And the way we know that, by the way, is we have electrons as a product, like they are being given off or being lost. So if you look at a reaction and you see electrons on the right-hand side of the arrow or the product side, It is considered a oxidation half reaction because, again, we think of it like electrons being given away. When we look at the second one, this is the reduction half reaction. And what we see is electrons are actually on the reactant side, like they're being gained by the reactants. And that indicates that what you're looking at is a reduction half reaction. They're frankly called half reactions because if you add these guys back together, these electrons cancel and you end up with the overall reaction that is taking place. Now you may be asking, why is there 4 electrons in this? And it's 4 electrons because each magnesium will lose 2 electrons, and there's 2 magnesiums, so 2 and 2 is 4. Total electrons are being transferred, 2 from each magnesium to each of those oxygens that are there. Basically, we'll pick up 2 electrons, and that's why each of the oxygens end up, 2 of them, with a -2 charge as well. Any questions on that there? All right, we're not going to talk about nonmetals here, the other definition of it. So as we've been talking about, we have our 3 ways to class reasons why a reaction takes place. And we have those 2 big classifications. So once again, we're going to now talk about more specific ways, again, to classify reactions. The first one is what we saw there, which is a precipitation reaction. So again, a precipitation reaction falls under the double displacement umbrella. And again, I know this is a double displacement because it is the only type of reaction pretty much where you start with 2 ionic compounds. So if you got 2 ionic compounds, you have a double displacement reaction happening. And again, that should result in pretty much one of 2 things occurring. Either you're going to get a solid or you're going to get water formed. So in this case, when we do get a solid, which is barium chromate here, the formation of this solid, which is a precipitate, makes this, again, a more specific classification of a precipitation reaction. And again, always in a double displacement reaction, we have our partners swapping places here. It is really important, as I might have mentioned last time, when you do this, and it's a very common sort of error, if you will, that if you're given something like this where you need to kind of predict what's on the other side of the arrow, you want to again make sure that you start with the correct formulas. So you just want to think about the basic ions that make this up. That's potassium from group 1, and that is chromate with a -2 charge. Basic units that make this guy up is barium with a +2 charge and nitrate with a -1 charge. I am at this point not concerned at all about the balancing part of it. I just want to make sure I get the right formulas. So when these guys switch partners and these 2 guys come together, once again, we get a formula of KNO3, just like nomenclature, +1 -1 equals 0. We do not get what commonly people like to write, K2NO3 2, because they see the 2's on the other side. So that is incorrect. You don't want to balance it and write the equation. You want to get the formulas first and then balance it. Also, why when we take this guy, which is +2, and put it together with this guy, which is -2, we end up with our proper formula here, BaCrO4. Now that you have all the proper formulas down, now you should be really concerned with balancing it and changing the coefficients. So that is, again, always the order you should do it so that you get it balanced and you get the right formulas here. And then obviously we need probably like a 2 there, and I think that might be it. And now we're balanced. So again, it's a super common error. People try to like balance it and write the formulas at the same time. You're always going to end up probably in a bad situation as a result of that. This one we saw earlier as well, which is our acid-base reaction, also still a double displacement reaction. Again, positive, negative, and again, we're just going to switch partners here, going in this direction. So now we're going to talk about, though, ways to classify redox reactions more specifically. So again, our redox reactions are electrons being transferred, and that is this case right here. Again, we have 0, +1, and -1 when they come together. So again, this is a redox reaction where if we go to our number line, we have lithium that starts at 0, ends at +1, becoming more positive, as we would expect here. That is being oxidized. Our fluorine starting at 0, ending at -1, and going in that direction, more negative, that is being reduced in this case. So it is clearly a redox reaction occurring. Again, electrons are really being transferred from the lithium, in this case, to the fluorine. This, though, as I zoom in, can also be called a single replacement reaction, the one on the bottom. This is also called a synthesis reaction, as we will see in a second as well. So this is a synthesis reaction, the top one. And that is when you take two things and basically make one thing, right? So a synthesis or a combination reaction, two things make one thing. There's our redox happening as well. Here on this one, this is what's referred to as a single replacement reaction. Some people call it a single displacement reaction. Some people call it a single exchange reaction. This reaction happens always when you have A plus BC. This is one ionic compound, and this guy could be a metal with no charge. And if it is a metal, it will come in and kick out the positive guy in this case. The result of that is you will then make a new ionic compound, and that guy that it kicked out will come out and actually have no charge as well. You could also do this reaction with nonmetals, which you probably did back when you did the halogen one with the different layers, if you remember perhaps that experiment. If this is a nonmetal, has no charge, it will actually come in and kick out the negatively charged guy. That's because a metal typically becomes positive, so it kicks out the positive guy, and a nonmetal typically becomes negative and kicks out the negative guy, basically. The result of that is, again, you're going to get a new ionic compound formed, and whoever gets kicked out will end up with no charge. And that's what we see here. The zinc's going to come in. It's going to kick out the hydrogen. Hydrogen comes out by itself naturally as H2 gas. That's the bubbles that you see. And then the zinc now gains a charge and hooks up with the chloride here, and that is a single replacement reaction. In these type of reactions, whatever is coming in actually needs to be more reactive than what it is replacing. So for example, if you did this exact same reaction, but you popped in there copper instead, you're going to get no reaction happening because copper is actually less reactive than hydrogen, and it actually will not replace the hydrogen in this particular case. Now, this particular reaction here, go back here, I think. This particular reaction that we're talking about is still a redox reaction. And if we take a look at it here, get rid of all that. When we look at the zinc on the left-hand side, that is zinc by itself, no oxidation state. The hydrogen here in hydrochloric acid is +1. The chloride is -1. On the right-hand side, the hydrogen is 0. That is naturally how it comes, so it has no charge, uncombined. The zinc over here now has a +2 charge, and the chloride has a -1 charge. So if we take a look at our number line here, the zinc started at 0 and ended at +2, which means it's moving in a positive direction. It is the zinc here that is being oxidized. The hydrogen actually started at +1 and ended on the right-hand side at 0. So it is moving in the negative direction. It is actually the hydrogen here that is being reduced. What about the chlorine on each side? Did it change? It did not change. So it's -1, -1. The chlorine here is actually a spectator ion. So that's actually a spectator ion. It's hanging out, going for a swim, not really doing much in this case. You could actually write our net ionic equation for that as well to show you what's going on. So if we were to take this guy here, this reaction of zinc plus our 2HCl makes our 2H2 and our zinc chloride. If we wrote our total ionic equation here, we would have our zinc, which is a solid. Our HCl would break apart as it's a strong acid into these two guys. Our H2 would stay together because it is a gas, so we wouldn't break it apart. And then our zinc chloride would break apart into zinc with a +2 charge, and I'll go underneath, and we would get 2 chloride ions here. When we look at it here, this is the only ions that are exactly the same on both sides. Now, some of you may think, isn't the zinc the same on both sides? Is the zinc the same on both sides? It is not, because on the left-hand side, zinc does not have a charge. On the right-hand side, it does have a charge, yeah? So they're not ions on both sides. So even though they're both zinc and they're both by themselves in a sense, they are not the same thing because one does have a charge and one doesn't. So our only spectator ion is actually the chloride, which gives us our net ionic equation in this case of zinc plus those couple of hydrogens going to form hydrogen gas and some zinc ions that are basically floating around in the solution. What's actually happening here is my zinc is going to send over a couple of electrons to the hydrogen ions. Each hydrogen ion will pick up an electron and become H2 as a result of that, and basically come out of solution as bubbles, as you see it kind of bubbling out of the solution, or bubbles that are formed in that case. Any questions on that there? Another sort of classification of reactions that do fall under redox is combustion reactions. And combustion reactions, I would say probably 99% of the time, if you're having a conversation about combustion reactions, not sure why you're having that conversation, but if you are having that conversation, you're probably talking about the organic combustion reaction, which is always you take an organic compound, which is pretty much carbon, hydrogen, maybe oxygen. You react some O2 with it, you get CO2 and water is pretty much always what you're going to kind of get out of that reaction. You can have what is sometimes referred to as an incomplete combustion, where you get carbon monoxide and water, but most of the time you're going to get CO2 and water. That's what happens when you light your Bunsen burner there. Methane plus some oxygen, a little spark. You get fire, CO2 and water. Also, dare I say, in the experiment where you turn the Bunsen burner on the bench. What's that part of the experiment? Yeah. And you saw hopefully condensation occur on your bench, right? And that's because water got cooled down really quickly, and that was the water condensation that occurred on your bench as it got cooled down from the cold bench. Hopefully you didn't set the place on fire either. So that is probably most of the time when you talk about a combustion reaction, what most people are talking about. But ultimately, if it is a combustion reaction, you frankly only need O2 involved. So O2 is really the only thing that you need involved for it to be a combustion reaction. That means, for example, if we take a look at an equation that we saw a couple of times already, magnesium plus oxygen makes your magnesium oxide that you got there, that white solid. This reaction, as we talked about before, is definitely a redox reaction because there's electrons being transferred. It is also, once again, two things that make one thing, which means it's a synthesis reaction or a combination reaction. And dare I say, I see oxygen there, which means it's also a combustion reaction as well. So as you can see, this one particular reaction, you could actually classify 3 different ways depending on sort of what you're looking at. I would say most people would probably go with the synthesis classification, although I think your lab goes with the combustion identification there. But again, you can definitely classify reactions in multiple ways depending on what you're looking at. We saw the same thing when we talked about double displacement reactions, which also can be classified as a precipitation reaction if you make a solid. Double displacement reactions also could be an acid-base reaction if you make water, right? And you have an acid and base involved. So there are multiple ways you could classify the same reaction. Speaking of synthesis reactions, officially here, we kind of stepped on it a little bit earlier. Synthesis or combination reaction is pretty much when you put something together. So once again, that is your classic sort of form of it. Two things make one thing. So the formation of water here, two things make one thing. Formation of sodium chloride, also a synthesis reaction. Once again, sodium chloride reaction on the bottom is a synthesis or combination reaction. And again, also is a redox reaction that's happening. So again, can be classified the same way. Synthesis and combination are redox reactions, ultimately of what's going on. We have maybe the last type of classification, which is really the opposite of synthesis or combination, and that's a decomposition reaction. In a decomposition reaction, you basically take one thing and you break it apart into two or more things. So we got water going to hydrogen gas and oxygen gas. Again, with your 9-volt battery there, a little bit of bubbles happening, hopefully in those little test tubes, and you run electrical current through it, you could break it apart. If you take something like, not that, you take something, yeah, maybe that, H2CO3, a little carbonic acid, it will very quickly decompose into water and carbon dioxide gas. You get that plop, plop, fizz, fizz, Alka-Seltzer type of deal. And you'll see those bubbles sort of happening. These are still redox reactions. And again, when you look at something like the water sort of example here, on water, this is +1 and -2. This is 0 and 0. So when we actually break apart water, going in this direction, hydrogen starts at +1 and ends at 0, becoming more negative. So in this case, the hydrogen is being reduced. The oxygen starts at -2 over here and ends at 0, becoming more positive. It is being oxidized in this case. And that's opposite, obviously, of what's happening when you put it together. So when you go the other way, those two things basically switch around and being oxidized. Question on that there. So decomposition reaction is when you start with one thing, break apart into multiple things. It is still a redox reaction. Now, just to summarize what we've been talking about in terms of classification, again, we have the big classification of double displacement, which under that big classification of basically two ionic compounds switching partners, making new ionic compounds on this side. We have more specific classifications of precipitation reactions, where we make a solid or a precipitate, and acid-base reactions, where we make water, basically, acid-base neutralization reactions. Just so we're also clear, there's absolutely positively no electrons being transferred in a double displacement reaction. The charge on the left-hand side for those elements and the charge on the right-hand side for those elements are exactly the same. So there is no change that occurs. So just an example, like the HCl plus the sodium hydroxide goes to our water plus our sodium chloride. That is +1 here, that is +1 there. That's -1, that's -1, that's +1, that's +1. That is -2 for the oxygen, -2, and that guy's still +1. So there is no changing happening of oxidation states. There's no electrons being changed. The sort of charge of these things in double displacement reactions don't change as they go from one side to the next. Those ions basically kind of stay the same in terms of their charges on each side. And that is different than what we have in a redox reaction, where It's all about transferring electrons. And again, redox is the big sort of category for which you can more specifically classify a reaction as a synthesis or combination reaction, where two things make one thing. You could do a decomposition reaction, where one thing makes two things. You could do a combustion reaction, where you basically have O2 is really the only thing that you need. And lastly, you could have a single replacement reaction where you have one thing that has no charge, could be a metal or a non-metal, and you have an ionic compound where this guy comes in and kicks out, making a new ionic compound, and again, that guy comes out with no charge. By the way, how do you know if this reaction is going to take place? Like I said before, some things has to be more reactive, whatever's coming in for this reaction to take place. You sometimes will come across in books and stuff what is referred to as an activity series for your single replacement reactions. The basic activity series is a bunch of elements listed and hydrogen somewhere in the middle. And when you look at this list, anybody that's higher on the list will actually replace anybody lower on the list, and anybody lower on the list will not replace anybody higher. So if you look, you would see zinc higher than hydrogen, which means zinc would be able to kick out hydrogen. You would look on this list, you see maybe copper that is actually lower than hydrogen, which means it would not be able to basically come in and kick it out. This guy would be able to kick it out because it's more reactive. By the way, if you did this with nonmetals, the activity series is pretty much group 7. If you remember that experiment when you did those halogens, you looked at the reactivity of group 7. Reactivity increased which way in group 7? As you go up, yeah? So if you had fluorine, it would be able to kick out chlorine. If you had chlorine, it would be able to kick out bromine and so forth. But if you had iodine, it would not be able to kick out anybody above it. So actually group 7 on the periodic table for the halogens is its own activity series. Again, anybody in group 7 higher in group 7 would be able to replace somebody in that single replacement reaction with somebody lower, but anybody lower would not be able to replace. Much like you saw in that experiment when you got to the iodine part, no, it didn't replace anybody. It stayed purple basically up on top, and that's because it's less reactive than anybody else there in group 7.